Hi everyone, in this video I'll do one more follow-up example from the first part of 3.1. That was the part where we looked at the power rule and the other rules that were listed at the end of the video. So I'll start with that since I didn't include it in the last video, and then we'll move on to looking at derivatives of exponential functions. Alright, so carrying on from the last video, I'm going to consider the function f of w is equal to 2w squared minus 1/4 w cubed minus the cubed root of w. All right, so big tip that I have to give you is always change your roots into something with an exponent. So should remember properties of exponents. When you have a root, like a cubed root, it's w to the 1/3. If it's a fourth root, w to the 1/4, so on and so forth. So I can go ahead and make this switch here, and that makes it way easier to take my derivative. So now if I take my derivative, f prime of w, I know by the sum and difference properties, I can take these three derivatives separate. So if I wanted to denote that, I could say, okay, I can take the derivative of 2w squared, subtract the derivative of 1/4 w cubed, subtract the derivative of w to the 1/3. All right, and then I'll finish my calculations, focusing on this first piece here. 2 is a constant multiple, therefore I can rewrite that. The derivative of w squared is 2w to the first power by the power rule, so drop the constant down. In the exponent, 2 minus 1 is 1. Okay, minus 1/4 is a constant multiple, can keep that here, times, okay, I can drop the 3 down here because, again, I can use the power rule, so I have 3 times w to the 3 minus 2, which is 1. Or sorry, 3 minus 1, which is 2, my bad. Okay, minus, and now I need to take the derivative of w to the 1/3, so that would be 1/3 w to, okay, 1/3 minus 1 is negative 2/3. All right, you should at least simplify the basic stuff here, so do your multiplication, why not? 2 times 2 is 4, w minus 1/4 times 3 is the same as 3/4. We have w to the second. Okay, minus 1/3 w to the negative 2/3. All right, so keep in mind, like I said in the previous video, at the end of it, the book will absolutely make you simplify this part, so you do not have to do this for me, but what you would have to do book-wise is change this into 1/3 times w to the 2/3. Then you'd have to change this bottom piece into 1/3 times the cubed root, okay, 3 is in the denominator, so cubed root of w squared, and then I think they make you rationalize too, I'm not sure, but I think you get the idea. So it's a lot easier to just leave it like that, and honestly, gives you way less room for error, which is kind of nice. Okay, so again, note from last time, you're gonna have more algebraic steps sometimes, and it can make you simplify sometimes, but generally, you should be able to do that and use these properties, at least in this section. Okay, so main thing I wanted to get to in this video was taking derivatives of exponential functions. I'm going to give you a partial explanation of the technique we use for exponential functions, and in order to do that, I need you to remember a couple of exponential properties. All right, so first, if we have the function b times a to the x. I know this is exponential because b is just a constant multiple. I don't really need to worry about that, but this is because I have a constant raised to a variable. All right, so recall when we have an exponential function, we have a constant raised to the variable. If you see this, it should clue you in, I can't use the power rule, it's not the same thing, gotta use something different. Okay, so now let's simplify this a little bit and consider the function f of x equals a to the x power. If I run u plus v through this function, meaning I plug u plus v in where the x's are, I would get f of u plus v is equal to a to the u plus v. So I just ran u plus v through the x. Okay, so this is equivalent to, by properties of exponents, a to the u times a to the v. So if you have one base raised to something added, it's the same thing as multiplying two bases raised to each power. Okay, so these are equivalent by properties of exponents. If we were in Math 99, I would go through and explain why that's true, but for now, I will not for our purposes. Okay, so now, again, we want to take the derivative of this exponential function, a to the x. We know all derivative shortcuts stem from the definition of a derivative. That's what I've got going on right here. Okay, so if I want to take the derivative of this function, I need to run the x plus h through the exponent, okay, minus my original function, a to the x over h. So this is just applying the definition of a derivative. All right, now by what I showed above here, properties of exponents, when I have a to the x plus h, that's the same as a to the x times a to the h. This minus a to the x just stays the same. Okay, here I'm going to factor out a to the x. All right, notice that if I can take the limit across multiplication. We've talked about that already. So if I take the limit as h goes to 0 of a to the x, okay, the h is not going to impact that at all. All right, so since the limit does not impact that a to the x, what we can do is pull the a to the x out in front of the limit, and then we're left with the limit as h goes to 0 of a to the h minus 1 over h. All right, so this one, there's not honestly a real nice simple algebraic way to get that out of it. I think I had to prove that formally in grad school, and it was a real you-know-what. So just tell you, if you start plugging in values for a here, you'll see the property that this term right here, ends up equaling to the natural log of a. So if you establish a pattern and just keep running the limit numerically and graphically, like we've learned how to do before, this is eventually what happens every single time. So we establish that pattern there. All right, so key thing right here. If you are taking the derivative of an exponential equation, that means an equation where you have a constant raised to a variable, it's going to take this form. All right. That brings us to e to the x, the coolest function in calculus. Okay, so e to the x is definitely an exponential function. That is because e is a constant. So usually when I teach this in person, people ask, well, why is e a constant? How does that make sense? All right, e is kind of like pi. Pi, really special, really significant number. They make books about the history of it. It's something that's seen commonly in nature, etc. E is the same thing. It represents the number 2.7, blah, 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 a bunch of decimals. So E is just some letter that ancient mathematicians chose to represent the specific decimal that's seen everywhere. Okay, so E is in fact the constant. That means when you see E raised to the x power, you have a constant raised to a variable, which means your properties of exponents and your derivative taking for exponents applies. All right, so if we take the derivative of e to the x following this convention right here, e is our constant, so we have an e where the a is, that's what that is. Okay, then here e is a constant, so we have an e where the a is. All right, well, the natural log of e is equal to 1. So fun fact, in case you don't remember this, the natural log function and e are inverses of one another. They undo one another. So the natural log of e is 1, which means that the derivative of e to the x is always e to the x. So derivative of the e to the x is itself. If I asked you to keep taking derivatives, if I said take the first derivative of e to the x, you'd say, all right, it's e to the x. If I said take the second one, you'd say still e to the x. If I said take the 1/1,000,000th derivative of e to the x, you'd get it e to the x. So kind of cool because it's always the same. Alrighty. Okay, so let's look at some examples involving this. Take some derivatives. Okay, we want to take the derivative of f of x equals 12 e to the x plus 11 to the x. I didn't specify to use prime or Leibniz notation, so I'll just use prime notation. So I have f prime of x. Okay, by the summation property, I can take the derivative of these separately. So 12 is just a constant multiple, pull that in front. All right, now I need to take the derivative of e to the x. Well, the derivative of e to the x is always itself, so I just have e to the x. Done. Super nice. Okay, write my plus sign. Okay, now I have the derivative of 11 to the x. All right, so some students will say, okay, so 11 is my constant multiple. No, no, no. 11 is not a constant multiple. It's connected to this x that it's raised to, so recognize, this is an exponential function. It's not a constant. That means that I have to apply let's see if we can see it, this property up here. So a is now my 11. So I have 11 to the x, right? So just running the 11 in where this a is here, times the natural log of 11. Okay, we'll leave it like that. Not gonna turn it into decimals. Another thing I didn't say earlier, but when you see fractions like this, some people will divide this and be like, oh, it's negative 0.67. Oh, it's negative 0.333. Don't do that. Okay, you need to be used to working with fractions. The reason for that is because many of you from this course are going into fields like engineering. All right, engineering, physics, application-based fields. You do not want to be constantly converting to decimals, because you get error in there. And if you're doing something like building a plane or a bridge or something with really complex parts, you model those with functions. If you have a bunch of decimals in there, not going to be good because you don't want rounding errors when you're trying to build something that's that specific. So get used to fractions. It's got to be something we're comfortable with. Okay, so natural log of 11, leave it. All right, let's do another one. So we're considering the function f of x is equal to 2 to the x plus 2 times 3 to the x. Let's calculate f prime. Okay, so we have f prime of x is equal to, okay, 2 to the x is again an exponential function. We have a constant raised to the variable, which clues me in on that. Therefore, my derivative is 2 to the x times the natural log of 2. Took care of that. Rewrite my plus sign. Okay, another huge common mistake here. A lot of times people will multiply this. Say, oh yeah, 2 times 3 is 6, so I have 6 to the x. All right, that is not the same thing. These aren't like terms. You can't just smash them together. They have to be separate. Try to avoid making that mistake. Okay, so 2 is just a constant multiple, which means I can rewrite it 2 times. Okay, 3 is an exponential function, so I use the exponential property on it. So I have 3 to the x ln 3. Question for you. Should I just go ahead and multiply the 2 and 3 here? You should think. No, it definitely can't do that. Not like terms. This is what you got. That's your answer. It's good. Leave it there. Okay, let's try. Looks like I have one more on here. So let's try one more. Okay, so we have the function y equals 2 to the x over 3 minus root 16 to the x power. Okay, so let's rewrite this. It's looking kind of sloppy how it is right now. Not easy to take the derivative in this format. This is the same as y equals 1/3 times 2 to the x, right? So technically 2 to the x is over 1, multiply across the top, across the bottom, get the same thing. Oops, I should draw my little arrow there. Okay. Okay, so then we have the minus sign. Okay, this is root 16, and I believe that is all raised to the x power. So the square root of 16 is 4. That is to the x power. Simplified it, looks a lot nicer. Let's work with it now. So I want to calculate dy dx, or in other words, the derivative of 1/3 times 2 to the x minus 4 to the x. Right, let's calculate. So 1/3 is a constant multiple, can pull that out. 2 to the x, I have a constant raised to a variable. Exponential property applies. Okay, so I have 2 to the x times ln 2. Right, hold my minus sign. 4 to the x, I have a constant to a variable. Exponential property applies, so we have 4 to the x times ln 4. Okay, so that takes care of this part of the notes. No doubt your homework's gonna get a little bit tricky, a little bit more tricky than that. Okay, take it step by step. Promise you, you have the underlying foundation, the calculus foundation that you need. The only thing that could be a little bit tricky is the algebra stuff that they throw in there. So be on the lookout for that. Shouldn't be too surprising after what you had to do for 2.3. Absolutely ask follow-up questions, come to office hours, up to an appointment if you need to. Okay, thank you.